Hello everyone, let's talk about an optimization problem today. We have a right circular cylinder that's inscribed in a cone with height 4 inches and base radius 2 inches. And we are going to assume that one of the bases of the cylinder is on the base of the cone. And we want to find the largest possible volume of such a cylinder. And now the question is, how do we put the cylinder in the cone? And if you just think about it, there are actually infinitely many ways that you can put all kinds of cylinders in there. So one typical situation is that we have something that looks like this. Okay, so that's a typical situation, but you can actually adjust the base radius and then also adjust the height to change the dimensions of the cylinder, and then it's going to look different. So let's go into a more extreme situation here where we have a tall cylinder, but that's also thin. And so as you can see here, if we change the cylinder from this typical one to a tall cylinder, and then we are going to have a larger height. In that case, that's going to affect our volume, right, for the cylinder. But at the same time, as you increase the height, what happens to the radius? The radius will actually be reduced, right? So you can see that that can also affect your volume. So now the question is this typical one larger or is this tall cylinder larger? We actually have no idea because we have no information, right? We do not have enough information for this. We can actually go into look into another extreme situation where we have a short cylinder, but it's really wide. As you can see here, the base radius is going to be larger than both of those two previous cases that we were just looking at. But then this time, the height is going to be a lot shorter than those two. And then the question is, can we tell that this one has a larger volume than those two, or we have no information? And actually, we do not have any information about that. So that's why we need to do some calculation and see what kind of cylinder that we can put into this cone that will yield the largest possible volume. Okay, so now let's just focus on the typical one, and then we can see what's going on. So first, before we start doing the problem, before we start looking into the problem, we need to do some labeling on here so that we understand what the whole situation is, right? And then how things are affecting each other. And then also we have something to work with. And so first we are going to label the radius, the base radius of the cylinder to be R. Okay, so let me do that. So the base radius, and just put a dot there, and then the base radius, and then we put that as R. Okay, so that's R for the base radius. And then there is actually the base radius for the cone also, right? So we also should label that. And let me just label that in a different color right here. And then the base radius for the cone is going to be 2. That's given the problem. So let me just label that right here. Okay, so far so good. And then we also need to look at the heights, right? Because the heights can also be affected. So I'm going to label the height for this cylinder to be H. So let me just do it on the side. Okay, and then all the way to the bottom. And then we say that the height would be H, right? So we just label that as H. And then also we need to label the height for the cone. So right there, it looks correct to me, but okay. And then the height for the cone is going to be 4. So we just label that as 4 because it's fixed, right? It doesn't really change. And so for quantities that we actually have no idea, or for quantities that we can adjust, we are going to use variables to label them. But then for quantities that we are not going to be able to adjust, then we are going to label the actual numbers on there. Okay, I also need to do something on the diagram itself just to help me figure out some details on the problem. So what happens is that we are going to, let me just label this here. So if I label with a dashed line segment, okay, so that dot looks a little bit off, but that's okay. So we are going to just make it here. And then now what happens is that we are going to label it this way. Okay, so now after doing the labeling, then you can see what's going on. We need to find a way to relate R and H. So usually we use an equation to give a relation between the R and the H. And then you may say, why do we want to do that? It's really because when we change the height to be longer, then we have to shorten the radius. And on the other hand, if we make the radius longer, then we need to shorten the height. So there is one change of the quantity will affect the change of the other quantity when we try to figure out what kind of cylinder that we put into the cone. And so in this case, first thing that we need to do is to find a relation between the R and the H and see how one affects the other. Okay, so how do we do that? We are going to look at two similar triangles and then set up a proportion to relate the R and the H. Then that's why I actually drew those dash line segments on the diagram that we have here. So now let's just copy the diagram on the side with just those key information on there, because there are way too much information that we do not need on this diagram. So let's make a new diagram with just these important information that we need. Okay, so how do we do that? First, you can see that there is a line segment that's going down from the vertex of the cone to the base of the cone, right? So let's just draw that first. So if I draw that, then I'm going to just get that. I'm going to use the same color here. So that's just that line segment. And then we also have this base right here. So we are going to just draw the base. And then remember, those two line segments are going to be perpendicular to each other. Okay, so that looks good. And then we are going to draw this hypotenuse right here, right? I want this hypotenuse so that I can have a right triangle. So let's do that. Okay, so I get a right triangle, but that's not finished yet. Remember that I also drew a line segment right here, and I also need that line segment because I want two similar right triangles. So now I have two similar right triangles, and then you may say, which two, right? So let me label the points first. I'm going to label this point as A. Actually, it doesn't matter, right? You can label them any way that you want. So we can do like a B here, and then we have a C here, and then there was a D here, and then there was an E here. So I label all of them. And so as you can see here, the triangle ABC, right, this triangle right here, ABC, is similar to the triangle, the larger one, which is ADE. Okay, so because the corresponding angles are the same, as you can see here, even though the corresponding sides are not equal to each other. Their lengths are not equal to each other. Now, let's label the RH and then the 4-2 on here. And then so we know that the R, okay, so the R is right here. And then the 2 is at the bottom, right? That's the base of the larger triangle. And then we have the height. The height is actually what? It's the distance between B and D. So H is actually just right here. And then you may say, what about the 4? The 4 is actually the distance between A and D, is actually the length of the line segment AD. So let me just Let's draw that again. Actually, I don't need to draw the whole labeling again. I can just copy and paste, right? So with that right here, you see what's going on here. Now, um, let's say if I want to find the height for the triangle ABC, this is the height, right? The base is R. The height is actually AB. How do I get AB? I use the total, which is AD, and then I minus the BD, then I can get the AB. So I'm going to get what? This is going to be 4 minus, right? Minus H. Yeah, so AB is actually having a distance of 4 minus H. Now we can start setting up a proportion. How do we set up the proportion is actually quite simple. So we first can set up the ratio of the base, I mean the height of the larger triangle over the base of the larger triangle. So that becomes what? If you just write down a fraction right here, then it's actually just the 4, okay? And then divided by the what? The 2. So that's simple, right? That's okay. And then now that's equal to what? That's equal to, now because I put in the numerator the height of the larger triangle. So for on the other side of the equation, when I put down my numerator, I need to put down the height of the smaller triangle, which is AB. And we did the calculation here, which is 4 minus H. So we get 4 minus H right here. So it will be 4 and then minus H. Okay. And then you may say, what about the denominator? On this side, we have the base of the larger triangle. And then on the right hand side, then we need to put the base of the smaller triangle. So we put an R right here. Okay, so now we set up an equation that will relate R and H. And so now what do we do? We are going to solve for R or H right here. It doesn't really matter which one that we solve for. So it usually it will be a good idea to solve for solve for R, but I actually don't think it matters. Okay, so anyway, so let's just solve for R. I think that will be easier in this case. Why did I say H? Because I was thinking to work with R in later on, but then I just realized that it will be easier to solve for R here because um, we when we manipulate this equation, and we have 4R, and then all we need to do is to divide by the R. I mean the 4. Okay, so let's do it. So we have 4R. That's equal to 2 times 4 minus H. Mm, we can multiply the whole equation by 2R to get rid of the denominators. So we are going to get this equation. And then we can distribute the 2. So we have 4R is equal to 8 minus 2H. And then now we are solving for R, right? So we are going to divide both sides by 4. So we are going to get 2 minus 1 over 2H. Okay, so that's what R is equal to. Now, because we're finding the largest possible volume, that's really just saying that, okay, we want to maximize the volume. Okay, and then if we are maximizing the volume of a cylinder, that means we need to work with the volume formula for a cylinder. In this case, it would be what? Do you remember the formula for the volume of a cylinder? That's actually V equals pi and then R, which is this R right here, pi R square, and then the H. Okay. Now, the next step is to find the critical numbers, and in here it will be a good idea, instead of working with too many variables, we can actually replace r by using this expression right here, so that we only need to work with h without having to worry about the r. So now we can substitute this 2 minus 1 half h into this r here, and then we get an expression just in h only. So let's do that. So we are not doing any calculus yet. We are really just making a substitution right now. So what do we have here? The pi doesn't change, and then the r is replaced, right? So it got replaced by 2 minus 1 over 2h, and then there was a square, and then there was also h on the outside. And then to avoid having to use product rule when we differentiate the function, we should really just expand this and then distribute the h. So let's do a little bit more algebra work. And then if you're expanding a square, then you are going to get what? 4 minus 2h, and then plus 1 over 4h squared, and then times h. Okay, what is the shortcut for expanding a square of the binomial? You can square the first term, square the last term, and then for the middle term, you need to multiply them and then double it. So multiply them, you get -1, and then double it, you get -2, and then the h, and then you have all that. And then now distribute, right? So distribute. I will just keep the pi in the front because the pi is really just a constant. But I want to distribute the h so that I don't get a product of two functions. So I'm going to get 4h minus 2h squared, and then plus 1 over 4h cubed. Okay, so that's what we have right there. Okay, next step, we need to take the derivative now. This is actually our objective function because this is the function that we are trying to maximize here. Then you may say, what about the other function? The other function, it's really just giving you a substitution on the r, and also that can also be considered as a constraint function, because once you have chosen an h value, then your r value will get affected, right? So, and then based on here, you cannot choose a h value that's too large, as you can see here, because once you choose h to be a number that's greater than 4, then you're going to get a negative value for r. So you know that h cannot be greater than or equal to 4. But anyway, let's continue with the problem. So let's take the derivative of the volume, right, with respect to h. Then we are going to get v prime. I'm not going to write dv dh. You just need to know what I'm doing right here. I'm differentiating v with respect to h. Then I'm going to get, okay, so we don't need to worry about the pi, right? So just leave the pi for now. And then we take the derivative, which will become 4. And then 4, and then minus what? Minus 4h. Okay. And then plus 3 over 4 h squared. And then next step is to do what? Next step is to do to find the critical numbers, because those may be our potential maximum values, or sometimes the minimum values. Okay, so let's find critical numbers. Yeah, so there are two cases. One of them is when v prime is equal to 0. So in this case, we are going to get pi times what? 4 minus 4h plus 3 over 4h squared is equal to 0. So we need to solve this equation. We actually have no idea whether this equation is factorable, so we can use the quadratic formula, but then I will still just want to try it and see. So regarding solving the equation, we don't really need the pi, and we also can multiply everything by 4. So we actually can turn the equation into, if we multiply everything by 4, and then I am going to bring the quadratic term in the front at the same time. So if I multiply by 4, I'm going to get 3h squared. And then you may say, where did the pi go? We are dividing by the pi at the same time. And then I multiply the linear term by the 4, so I'm going to get negative 16 pi h. And then I'm going to multiply the constant term by 4. I'm going to get, what is that? That's 16. So we get this equation right here. And if we're solving this equation, we can factor it, right? Actually, we can factor this. How do we factor? Let's just do the quick check right here. We want two numbers that we multiply to 3h squared. So one of them should be h. The other one should be 3h. Okay. And then what about the 16? We can try 4 and 4 and see what's going on here. So we can do 4 here and then 4 here. Now let's do a quick check. H times 3h, 3h squared. H times 4, 4h. 4 times 3h, 12h, which can give me 16h. And then 4 times 4 is 16, so that's okay. And then now we just need to worry about the signs. Since we get a positive 16 as the constant term, then we need both signs to be the same. So either they're both positive or both negative. In this case, we want them to be both negative because for the middle term, we are having negative 16. So we should have a minus sign right here, and then we should have a minus sign right here. And so now we get two critical numbers right here. So we get h to be equal to 4, and then h is equal to 4 over 3. Now, remember that I just mentioned earlier that when h is equal to 4, what happens? We get 2 minus 1 half times 4. So think about plugging in the 4 in here. 4 times 1 half is 2. 2 minus 2, we get 0. So r is 0. That means what? The radius is 0, but that's not okay because when you are constructing a cylinder in the cone, we cannot really have the radius being 0, so that's not okay. So that means this is not something that we want. Okay, so maybe that's the one that we want here, but then we don't want this one, so we can and just keep that in mind, right? Just make a note somewhere just to remind yourself. So make a note here. No, if h is equal to 4, then r is equal to 0. So that's not okay, right? So remember that. Okay, anyway, let's continue with finding the critical numbers. We also have a second case right here. By the definition of the critical numbers, that's when v prime does not exist. But you know that's impossible. It's really because we get a polynomial function right here for the v prime, right? So there's no x value for this case. Okay, now once we have finished finding the critical numbers, we can start making the sign analysis chart. Okay. So let's do that. So we're going to find the sign analysis chart. Then let's do some labeling on there. So this is the x-axis. No, actually this is the h-axis, right? And then, so you know that h cannot be 0 or any negative number because that's a height, right? So we are going to start from 0. And even though 0 is not really a critical point in this case, but we are going to not consider anything on the left side of the 0. And then we are going to put in our critical number 4 over 3 here. And then we also have the 4, which is another critical number. And then we actually cannot really have anything on the right side of the 4. Okay. So now we only have two intervals that we need to check. One is between 0 and 4 over 3. The other one is between 4 over 3 and 4. So let's just do the checking right here. So I'm going to pick a number. In this case, we can pick 1 because 1 is less than 4 over 3. We plug it back into our first derivative, which is right here. And if we plug it back in here, then we plug the 1 in here. So we are going to get 4 minus 4 times 1, which is just 0. And then we plug the 1 in here. That will give us a positive number. So that's positive. And so that means the function is going to be what? It's increasing from 0 to 4 over 3. And then we pick a different number here. What is a good number to pick? We can pick 2 because 2 is greater than 4 over 3. And then if we put the 2 in here, then it's going to be what? 4 minus, and then what is that? 4 times 2, right? 4 times 2 is 8. So 4 minus 8 is negative 4. Then put the 2 in here. What do we get here? 2 squared. That will give you 4. 4 cancel out with the 3. Cancel out the 4 here, so you get the 3. So 4 minus 8, which is negative 4, plus 3. Negative 4 plus 3 is a negative number, so we get a negative number right here. All that can actually be done using a calculator, or you can plug the 2 back in here, which will be easier for you to get the sign. But make sure that when you put it in here, you did not divide by any negative number at the beginning, because that can affect the sign. So this is not our original v prime. So you got to be careful when you're plugging in the number here and check the sign. Okay, so going back to the sign analysis chart, from 4 over 3 to 4, the function, the v, right, the volume function is decreasing. So where do we get the maximum volume here? We are getting the maximum volume at 4 over 3. As you can see that there is a local maximum at that location. So now you can say, so based on the sign analysis chart, v, right, the volume function has a local maximum at x equals, what is that, 4 over 3? Or actually not x, right? I just keep saying x. It's actually h. Now, based on the what? Based on the first derivative test for absolute extreme values theorem, okay? So we say that since v is continuous and h equals 4 over 3 is the only critical number, we say that v has an absolute maximum at h equals 4 over 3. So now what? So now we can find the volume, right? Because we are trying to find the maximum possible volume for the cylinder to be in there. So what can we do? We can plug this h back into our volume function. Where is that? That's actually this function right here, because we already write the whole function in terms of h, right? There is no more r in there. So we actually don't even need to bother finding the r. So we can plug this h equals 4 over 3 back into all those h's that we are seeing. Then we have our maximum volume. Okay, so let's do that here. Now, V is equal to pi, right? And then times 4h minus 2h squared, and then plus 1 over 4 h cubed. And then what do we plug in there? That's our 4 over 3 that's in there, right? So plug the 4 over 3 in there. And then if you do all that calculation, right? I'm skipping all the basic calculation work. And then the answer is what? 64 over 27 pi. And by the way, don't do this on the exam, okay? And then now what do we have? That's the maximum possible volume that we have for the cylinder. And then if you want to find the dimensions of the cylinder, then you already have the h. All you need to do is to plug it back into um, this formula right here for the r to figure out the r. Okay, so that's it for this problem. So let me just write down the final conclusion for this problem. So we will say, thus, the maximum possible volume for the cylinder is 64 over 27 pi cubic inches. And then we're finished. Okay, so that's it for this problem. If you like this video or you find this video helpful, please subscribe to my channel and give me some support. Leave a comment if you can. Thank you. I will see you next time.